Guys, welcome to the next lesson on acidity of solutions, specifically the pH scale. In this lesson, we're going to be looking at the pH scale and the use of pH in measurement of calculating strength of acids and bases and the concentration of hydronium ions. In this section, pH will be discussed. pH refers to the concentration of hydrogen ions or hydronium ions in solution. So when I have a square bracket, it refers to concentration in moles per litre. As I already said here, pH is a measure of the acidity, which is defined by hydrogen ions or hydronium ions in a solution. Before we can go on, we must first understand that every time an acid or base is placed in water, the acid will either donate a proton or the base will accept. That will change the pH. But water itself will react too. So water molecules react with other water molecules in a reversible reaction, as we can see by the arrow here, which means it's not a very strong acid or strong base, but there's a reversible reaction. And in that reversible reaction, we have a water molecule donating a proton, as is the case here. Water donates a proton to form hydronium ions over here, and this water molecule will create a hydroxide atom. So water donates a proton, reversible reaction, it forms an acid, and it forms a base. These are equal in concentration. As we can see, there's a 1-to-1 ratio between them all. We can say pure water undergoes self-ionization, means it forms an acid and a base, and it's to a very small extent. So this doesn't happen to a great deal. So therefore, water is known to behave as a very weak acid, as the case here. Sorry, this one, of a very weak acid and a very weak base, producing equal concentrations of hydronium ions and hydroxide ions. If you look at this in a little clip video, you can see there's a glass of water, and we can see water molecules reacting with each other. It donates a proton in this case, and it donates so it forms hydroxide and water. And we also have hydronium formed as well as over here. So water is constantly reacting with itself to form hydroxide, hydronium, and water molecules. The concentration of hydroxide ions in water, when it's a pH of 7, when it's neutral, as in the case of water, is actually 1 times 10 to the negative 7 molar, or this number here. So it's a very small number, the concentration of hydroxide ions. Similarly, the concentration of hydronium ions is also very small. It's this number again. So experimentally, at 25 degrees Celsius, the concentration of OH and H3O, when we multiply them or sum them together, they equal this number. We can see, multiply the two together, and you get 1 times 10 to the negative 14. So there's the concentrations in mole of hydronium and hydroxide, and then here's the concentration of water at pH 7, 25 degrees Celsius. I've already summed this up. Hydronium ions form through the reaction of water as well as hydroxide ions, and these must be constant at pH 7. So the concentration is equal to 10 to the negative 7 for each of them, therefore 10 to the negative 14 for both of them together, which is what this slide summarizes also. So we can say that pure water and neutral solutions have equal concentrations, which is shown by the square brackets, equal concentration of hydronium ions and hydroxide ions, which is 10 to the negative 7, both of them. Whereas acidic solutions, the concentration of hydronium will be less than 10 to the negative 7, and the concentration of hydronium will be greater than. So this will be a larger number. There'll be an increased concentration of hydronium, and acidic solutions, there'll be a decreased concentration of hydroxide. Similarly, for basic solutions, there'll be a decreased concentration of hydronium, and there'll be an increased concentration of hydroxide, which is shown exactly what here is. The concentration of hydronium is greater than hydroxide in acidic environments, and the concentration of hydroxide is greater than hydronium in basic environments or alkaline environments. And when they're neutral, they're equal. So summary is, the higher the concentration of hydronium, the more acidic it is, which is shown here. We've got more H+, which is the same, it's the same as hydronium, these terms can be used interchangeably. The red is hydronium or hydrogen ions, and there's a greater concentration which refers to a lower pH, which means it's more acidic. Similarly, when there's less hydronium ions or hydrogen ions, there is a more basic solution, more alkaline solution. And when they are equal, we have a pH of 7, which is neutral. Let's do a calculation of pH. First of all, though, we need to start with calculating concentration. So we looked at this formula before, where the constant of water refers to the concentration of hydronium multiplied by the concentration of hydroxide. That will give you 1 by 10 to negative 14 molar at 25 degrees Celsius. So we have a 0.1 molar concentration of hydrochloric acid at 25 degrees Celsius. We wanted to calculate the concentration of hydronium ions and hydroxide. Because HCl is a strong acid, it means it will completely ionize in water or dissociate in water, which means every single proton of here, every single hydrogen ion will dissociate or be accepted by water, which means HCl is a strong acid over here, and water is acting as the base in this case. Water will accept the proton and it will become hydronium. So we can see hydronium is over here and chlorine is over here. Because it's a strong acid, every single proton will donate to water, which means the concentration of HCl will be equal to the concentration of H3O. So if we have a 0.1 molar concentration of HCl, the concentration of H3O, or hydronium, will also be 0.1, which is what it said here. HCl completely ionized in water, there was 0.1 mole of HCl, and it will therefore produce concentration of hydronium as 0.1. This is true for every single strong acid and strong base. It will be the same concentration as the original product, original reactant. Now we can use this formula here to help us calculate the concentration of hydronium. Given that the concentration of these two multiplied together at 25 degrees Celsius, which is what the question is referring to, the concentration of them is 1.0 times 10 to negative 14 molar. So in order to work out the concentration of hydroxide, we simply rearrange the equation, or we can use this formula triangle. The constant is 1 by 10 to negative 14, shown here. We know the concentration of hydronium, therefore we divide this number, 10 to the negative 14, by the concentration of hydronium, and that will give us the concentration of hydroxide, which is exactly what's done here. 1 times 10 to the negative 14 divided by 0.1, which gives you 1 by 10 to the negative 13 mole. So we have a very small amount of hydroxide and a very large amount of hydronium, which makes sense because we have mostly an acid environment, which means we're going to have a large concentration of hydronium and a small concentration of hydroxide. As I mentioned before, pH is a measure of the concentration of acidity. So it's calculated using this formula, where it's negative log 10 to the power of H3O multiplied by the power of H3O. How this formula was derived will be discussed later. In your calculator, if you simply push negative value, then you push the log value, on your standard calculators, the base power will be 10. So you don't need to type in 10. You can already push negative number or negative symbol on your calculator, then hit the log symbol. That will give you log 10 already. And then you put the concentration of H3O in brackets, and that will give you the pH of the solution. So for example, what's the pH of a solution when you have a concentration of 0.14 molar? Express your answer to 2 decimal places. So first of all, the concentration of hydronium, we know that is 0.14. We simply place the negative symbol, then we put log into our calculator, and we put a bracket, 0.14, and that will give us the pH of the solution. That refers to how acidic it is. The reason we use a log scale is we are transforming the data. So here is the original data, and we want to transform it to make it more linear correlation. So that's what a log scale log transform does. Here we have a slightly more complex problem for calculating pH, where we're asked to calculate the pH of a base. You'll recall that pH formula uses the concentration of hydronium. So we actually need to calculate the concentration of hydronium first before we can actually calculate the pH. In doing so, we need to always write our chemical equation. So what's happening here is we've got barium hydroxide, which is shown like this. We're adding it to water, and that's forming this here. Barium ions form plus 2 hydroxide atoms. We had 2 hydroxide over here, and so therefore we have 2 hydroxide ions over here. So the concentration of the barium hydroxide over here is 0.05 molar. Now the concentration of the hydroxide ions, there's going to be twice as many of them. So we are actually going to have to multiply the concentration by 2. So it's 0.005 concentration multiplied by 2, which equals 0.01 molar. So the concentration of the hydroxide ions is actually double the concentration of what the solution was in this instance, because there are 2 moles of hydroxide ions that form. Now that we have the concentration of hydroxide ions, we can actually work out the concentration of hydronium using the same formula as before, where we have 1 times 10 to the negative 14, or 10 to the negative 14, and we divide that by the concentration of hydroxide, which will give us the concentration of hydronium. Concentration of hydronium ends up being 1 times 10 to the negative 12 molar, and now we can put that amount into our pH formula. So we have negative symbol, the log formula, and then we place in brackets 1 times 10 to the negative 12, which gives you a pH of 12. The final pH that's been calculated in this example is where we're calculating the pH of a solution at 25 degrees Celsius, but we're looking at a solid amount of a base being placed in 100 ml of solution. So to work out the pH, we need, of course, the formula negative log 10 of H3O, but before we can calculate the concentration of H3O, we must first calculate the amount in mole of what we have, because we don't know the concentration unless we have moles over volume with concentration, and we don't know the moles and we've got the volume. So we start back here. We find the moles of sodium hydroxide, which is 1 gram divided by its molar mass, which is equal to 0.025 mole. So we've got 0.025 mole in 100 ml of solution. Because NaOH is a strong base, it completely breaks up into water. And we can see that NaOH will form 1 NaOH molecule will form 1 hydroxide atom. So we can say that the moles of hydroxide is equal to the moles of sodium hydroxide. We have 0.025 moles of hydroxide. Now we're going to use the volume that we're given, which is 100 mils, and we've converted the volume, 100 mils, is equal to 0.1 litres. We've converted that into litres, and we've now divided 0.025 mole by 0.1 litres, which is equal to 0.25 molar, or 0.25 moles per litre. That's the concentration of hydroxide ions. And now again, we use the Kw formula, where we divide 1 times 10 to the negative 14 by the concentration of OH, which is 0.25, which will give us the concentration of hydroxide, which is here. And now we place the concentration of hydroxide into the brackets of the negative log 10 formula, which gives us a pH of 13.4. This is what you should be able to do at the end of this lesson, which is pH is a measure of the number of hydrogen ions, and you should be able to calculate pH using the formula negative log 10 H3O. And know that concentration of water is equal to H3O positive times OH negative, and you should be able to calculate these two. Thanks for watching.